Yeah, hello everyone. Welcome back to chapter 4. And in chapter 4, we're going to look into another system, another satellite subsystem, propulsion. I'm quite sure you've been exposed also to aircraft propulsion. There are some governing equations which is important, and also maybe in upcoming lectures, not lectures, but maybe more into another course that you're going to be exposed to, which is the launcher, where you will have also a bit of a propulsion, where all those governing equations will be discussed, especially for rocketry. But anyway, what we're going to actually look at the topic today is that an overall overview of a subsystem, which is the propulsion, and how this actually subsystem is going to help us in basically stabilizing our satellite, in orbit operation, etc. Yeah. Okay. Now, if you look at propulsion system in satellite, there is basically two major functions. Now, what are we going to actually do and discuss here? Further subjects like space mechanics, further subjects like uh, rocket technology, you will understand a bit more, I would say, in detail when we actually treat that subjects. But as of today, this is probably going to be a slightly like an introduction on the propulsion system for you. But I think more importantly, to understand the exact difference, why are we going to use the propulsion system in the satellite, and what is going to actually do for us. That is the main purpose of this particular chapter actually. So if you look at a satellite motion, let us define the satellite motion. We know we are going to actually inject satellite into the orbit, then there will be a motion. So there are very, very clear distinguished motion of a particular satellite or any rigid body in space. There are two motions, major motions, that we always define, or rather always look into: the rotational motion and the translational motion. So these are the two motions that we always have to talk about when you want to fly satellite. Now, in chapter 3, we have treated the rotational motion with the devices such as reaction wheel, momentum wheel, control moment gyro, even spin stabilized technique. That is going to actually dwell with, or rather, that's going to provide us with the rotational motion. So, but there are actually a system, for example, the propulsion system, where we can actually use it for the way we mount the propulsion system, or the thrusters, so to say, in our satellite, that can actually give us either rotational motion or translational motion, or it can give us both motions. So that is important to understand. So as you can see, rotational motion is basically you are at the same point and you will rotate. If you have three axes, you will rotate maybe along x-axis, y-axis, and z-axis. So you have three motions, and practically you are rotating. You are in the same spot, but you are rotating along the axis. And translation motion is basically all those three axes will be actually translated, or rather will be moved to another point altogether. So there is a translation action is incurred. So we must understand these are the two major motions. So what exactly happens in a satellite? And remember, the satellite being actually governed by these actually two motions, and these two motions are always actually telling us, look, are we in the right track? Look, are we in the right attitude or rotation? Are we in attitude means attributed? Attitude means it's always attributed to the rotational motion. Are we in a direct, in a good direction with respect to our orbit? That is a translation motion. So every time there is something disturbing, external disturbance, or rather the space, in a space environment, there are many disturbances the satellite, and when they actually start disturbing the satellite, what exactly happens? The way that actually we fly, it is going to be also disturbed. So let's say I'm standing still, something disturbs me, so I'm going to actually probably rotate around all the three axes. I need to stabilize that. Or somebody pushes me very hard, then I move from this spot to another spot, that's also disturbance. So these are quite typical in satellite motion. always satellite being when you fly a satellite, you will be disturbed. We will learn that a bit more detail in space mechanics. We will see that how this satellite is being, or any rigid body you put into the space, how, or in its orbit, how it is going to be disturbed and how we are going to actually treat that. So when that is done, so any disturbance you need to have a sensor, just like in aircraft. Assume that you want to look at the motion, the rotational motion, you will have a very simple or very common device or sensor, gyroscope. And I think you've been treating, or rather you've been exposed to gyroscope in your lab exercises. So that is quite typical for us to sense the rotational motion. You want to sense maybe the translation motion, then you should be using sensors like accelerometer, for example, that can actually help you to look at your translation motion, that it can be done. Or even your GPS can be also in place. Your GPS can be also giving you a coordinate, like say a new coordinate and old coordinate and a new coordinate if a translation motion is being detected. So there is always a sensor, and when we have a sensor, when we have the detail, when we know how much we have been disturbed and what are the disturbances available, what is the magnitude, all that can be calculated, and then we have a control logic within the satellite itself to help us to correct based on the mission requirement. Assume that we are supposed to fly in particular orbit, then the mission requirement will be injected into the control logic. You have to just do the comparison, and then the system helps you to control. So therefore, like the reaction wheel that we have studied, the momentum wheel that actually we have been exposed to, all these are basically is going to help us into rotational motion. Now, I will talk a bit more on the rotational motion in the upcoming chapter. There, I will introduce a bit more on that rotational motions, or rather the devices that you're exposed to. At the moment, just assume that for a rotational motion, there would be some sort of a wheel in the satellite which is helping us to rotate, or rather to move. It could be we call a momentum wheel, we can call a reaction wheel, or even a control movement gyro, that we will see that in an upcoming chapter. And another way, basically, we can induce a rotational motion or even translational motion. We can use that thrusters. What is thrusters? Thrusters is a propulsion system. It's an engine. So just like an aircraft, from point one to another point, you want to actually move, you on an engine. So translation motion happens. So likewise, let's say you have been disturbed in the rotational motion, then practically what you have to have maybe a propulsion system which can also help you to correct that rotational motion. So we will see that. So once that is done, then the actuator, these actuators are, in this case, this is a propulsion system, so actuators can be the propulsion system to help you to correct the satellite. So for this particular chapter, please understand that propulsion system is there to help the satellite to correct a particular motion. It could be a rotational motion, or it could be a translation motion from one point to another point. So that is the core, but you must understand the actual function of that subsystem. Now, this is something that you will understand a bit more, I would say, deeper when you do space mechanics. But I need to introduce this already in satellite technology. Otherwise, you wouldn't really appreciate the actual subsystem that we're talking about, which in this case is a propulsion system. Now, if you look at there are internal and external disturbances that you have in satellite. If you fly a satellite, internally there are some problems. That means there are some disturbances disturbing us, and externally through the space there are also disturbances. So both these disturbances are basically disturbing us. If you look at it, for example, temperature gradient, we have done in one of the subsystems that we have treated is basically power system. In power system, we've also seen that, well, temperature gradient will be there because we are going to the sun phase and then eclipse phase. Therefore, we need another system basically to help us in order to keep the temperature in a right regime. Therefore, we have treated thermal control system or other thermal system that help us to keep the temperature within the cooling. You have moving parts. You have, for example, to track the solar energy or the sun, you need basically a tracking device, a motor. If you have solar flaps that we have also seen in our power system or power subsystem chapter, we need to track. So you need to rotate with respect to that exact trajectory of the sun. So therefore, there's a rotating device in the satellite which moves, and it creates also disturbances internally. You have fuels. Propulsion system must have fuel. Okay, fuel can come out later. We will see what kind of fuel actually we can use. But if you have a liquid fuel, then obviously there's a problem of sloshing. Sloshing means if you have a bottle of water, you start shaking the bottle, then the water inside sloshing. Sloshing happens to the water. So therefore, it is it's something that you can't avoid it. But there are actually techniques. There are solutions for it. But even then, there are internal disturbances. Cross directions. Now, if you have control propulsion systems, you know that you need to on and off the system. That means when you on, you have the thruster. Just like aircraft engine, you on the aircraft engine and a full throttle probably, then you are going to actually thrust towards front. So, but if any misfiring happens, you may also introduce a different motion that is undesirable. So that also you need to treat. Then you have an external disturbances. That is internal. Then you have also external disturbances that we always talk about. Every of these disturbances you will see in your space mechanics or in another optional subject, spacecraft dynamics control. That's upcoming. But for today, you can see that atmospheric drag is there, disturbing our satellite. So for LEO, low Earth orbit, that means like flying laptop that we have done or we spoke about, small satellite missions, cube satellite missions, these are all low Earth orbit satellites, about 500 kilometers of altitude. It can go up to about 800, 900, it's still considered LEO, low Earth orbit satellites. So there are actually rotational and translation motions that can be actually experienced by this particular drag. So it also actually pulls you down, and at the same time it also rotates the satellite. So there are sorts of disturbance you must understand. Earth magnetic field, when you fly a satellite is full of electronic systems. There is electrical, we have learned that also. We have seen in a power system, we have cables running, and assume the cables are actually also governed by the Earth magnetic field. You put a cable with electricity, then you definitely would have a reaction. So Earth magnetic field also is going to disturb us. In LEO, it is going to cause us a rotational motion. You will see that. Gravity gradient. Now don't forget, gravitational law is always been applied to our satellite. For sure, gravitational law. So our satellite is flying, in fact, based on the gravitational law also. So due to that, there is also a disturbance from that gravitational field. So if you look at it, LEO is a rotational motion. You can see, when I say rotational motion, the satellite is basically almost like in one single spot, and it is actually rotating with respect to the three axes, X, Y, and Z. But with translation, it moves from one point to another point. So please understand that. Earth obliteness, this you will treat this in space mechanics in detail. This is it means that the Earth is not perfect sphere. So when it's not a perfect sphere, and you do have basically gravitational field, and you know if it's not a perfect sphere, so there is always the pull towards to planet Earth. It is not constant always. So there are, because of that, then you have Earth obliteness problems. J2, don't worry about it. This is actually quite predominant for GEO. What is GEO? Geostationary orbit, very high orbit, higher altitude, 36,000 kilometers. Most of the telecommunication satellites are flying there. If you look at maybe NASA, etc., it is flying at 36,000 kilometers of altitude. Don't worry about the orbits, we will learn soon. Solar pressure is another disturbance coming from the sun. Remember, the sun, it gives you the solar energy, so that your photovoltaic cells can generate, and then you can actually have electricity to run the satellite. By the same time, the sun is also disturbing the satellite. So there is a solar pressure. In Leo is rotational. In Geo is actually eccentricity drift that you can have. Don't worry about the actual disturbance in Geo, because this is more into space mechanics that you will treat in upcoming subject. Third body. Now, another problem that we have of course the satellite, we have planet Earth. Don't forget, we have third body. Third body means it could be actually a moon, it could be also sun. So there is always an interaction, gravitational interaction between all these actually bodies. So that is also disturbing satellite. All this can be quantified, and it is either is going to affect us translational or rotational motion. Now, these two motions, translational motion, please do understand, from one point to another point, there is only one system in satellite that can do this. Is just propulsion system. Full stop. Thrusters or propulsion system can provide that motion from one point to another point. You don't have any other ways actually to do that at the moment. Okay, so please understand that. Make it very simple. So if you think of a translation motion, you just think of propulsion system. That's it. You think of translation motion, just think of thrusters. Okay, in satellites, propulsion systems, you say it's thrusters because you give us a thrust. So we say it's a thrusters. But in an aircraft, you say an aircraft engine. We don't call it satellite engine. We say it's a thrusters, because normally if you look at it, it's a very compact, very small. Gives you the thrust. It's not an engine which runs always. Whenever you need it, then actually you on and off. That is the difference. You don't run propulsion systems like in aircraft. In satellite, when you need it, you on. Then if you don't need it, you just off it. So it's like on off always. One. All right. If you look at it, this is a very good comparison. I wanted to show space shuttle here just to make you understand that what difference is that between an aircraft and a spacecraft. Now, for us, a space shuttle is indeed a spacecraft. You can actually, it's a rigid body for us. We treat it just like one satellite, and all those problems the satellite have, satellites have, space shuttle actually we should also consider those kind of problems as well. So it is a rigid body for us. Now, if you look at it, the motion that I've talked about, let's say roll is a flight direction, even in your aircraft is the same. So when you want to move towards the X direction, you need a thruster. That means you need the engine. Engine is going to help you to propel and move the shuttle or even the aircraft. Now, if you look at the rotational motion always we say is attitude motion. So if you look at, I have 3 axes here. I can define my roll as X, my pitch as Y, and my Z as yaw. And my Z is always looking at planet Earth. So that's how actually the satellite or even the spacecraft flies. So the belly of the spacecraft, the belly of the space shuttle always actually is looking to your planet Earth. So a rotational motion along these axes is what we call an attitude axis. And these are in order to do this in satellite, we must have something is rotating inside the satellite. So we will see that in next chapter. So when I want to actually study, or rather when I want to look into the possibilities of how am I going to actually fly the spacecraft. Now, for a space shuttle, if I want to move the space shuttle from this point to, let's say, this point, I on the main engine. Space shuttle main engine is there. I on it. You can imagine this is also a satellite, for example. So I on it. It actually is going to fly. Now, if I don't want to actually do any translation motion, but I just want to actually make sure actually it is pointing in the right direction, there's a rotational motion. Let's say I don't want to face here, I want to face towards to you. I need to do a rotational motion. So with that, you look at the body of the spacecraft or the body of the satellite, the body of any rigid body, you will have thrusters. So imagine this. Let's say this is a cylindrical body. Let's say I have a thruster. which is facing downwards, and I have another thruster facing upwards. If I on both, what exactly will happen? You will have a rotational motion. Can you imagine? Fire same amount, fire same amount down, fire same amount up, you will have a rotational motion. So you are actually going to do rotational motion. But if you only fire only one, you are not going to actually have a rotational motion. Instead, you will have a translation motion. Okay, you have a translation motion. So that's how actually you start using the thruster systems, whether to do your attitude, which is, as I've said, the rotational motion, or orbit control means that orbit is a translation motion. So there are two functions that the propulsion system can give you. Got? Now this is just to tell you, normally if you look at a spacecraft mission, so there are, technically speaking, I've defined here main system and orbit correction system. So main system you should know already. When main system, I need to fly from planet Earth to a particular orbit. So that's going to be a main system. What main system should be? Should be giving me a translation motion. So let's say I'm firing. This is our translation motion. See, all these are translation motion. All these are translation motion. But when I start going into the orbit already, all this will be my orbit correction. It could be also rotational motion. When I'm done with my translational motion, it could be rotational motion. So main system and orbit correction system. Now, as you said, main system would be a propulsion system. Orbit correction system would be also a propulsion system. So now you see how and when the propulsion system is being used. Remember, when you want to fly from planet Earth to a particular orbit, the launcher is going to do the job. The launcher is also a translation system. That means there is an engine which takes us from one point to another point, just like an aircraft. When you are in the system or when you're in the orbit already, what exactly happens? The satellite would have its own propulsion system, which we call thrusters, in order to correct the actual translation motion. So that we will be in the perfect orbit. We will be in the perfect altitude. Okay? Now, since we have been talking about the two, this is I think all these satellite applications, we know satellite can be used for communication, navigation, meteo, Earth observation, astronomy, astrophysics. These are all applications. Now, orbits, you will know all these orbits when you do space mechanics. More importantly, now here, correction systems that I want to actually speak about. These correction systems that we have here is saying that whether I have an orbit or an attitude. So as I've said, orbit is a translation motion, attitude is a rotational motion. So if you look at it, all with the bracket, it is optional. Okay, if you look at it, that's an optional. So you can have gone next page also we have. Okay, all this basically it says that there's an option. Now if you look at it, that means the orbit system or the orbit motion is optional. But if you look at attitude motion, the rotational motion in any satellite, it is a must. That means you should be having the attitude control system in a satellite. Is mandatory for any satellite. It could be low cost, etc. It is mandatory. Rotational motion is mandatory. Translation motion, when it is operating in its orbit, it is optional. If you embark a propulsion system into the satellite is going to cost you more. It's always like that. So a propulsion system, you will offer a propulsion system when you have a very, very important mission, a long duration mission, 10 years mission, 15 years mission, 20 years mission. You will definitely 100% you will have a propulsion system on board. But if you have a mission for about a year or two, a low-cost mission, small satellite mission, CubeSat, you may not opt for a propulsion system because your lifespan is about a year or two. You will also start doing this or understanding this clearer when you do space mechanics, because there you can see how fast without a propulsion system the satellite can be dropping to planet Earth. That means dropping towards planet Earth. This is because of the disturbance that we talked about, for example, aerodynamic drag, etc. Okay, so nutshell for this, OTV, orbit transfer vehicle. Okay, these are all the space shuttle. You will learn a bit more on our satellite launcher technology or rocket technology course. What I'm going to give you here is that just to tell you that orbit motions, that means which requires a propulsion system, it is optional. But attitude motion, rotational motion, for any satellite, it is mandatory. So which means that if we don't want to actually use a propulsion system, we must have other systems basically in order for us to do, or rather in order for us to ensure that we can do a translation or rotational motion. We will see that in next chapter. Okay? All right. Important parameter. Now, this is a very, I would say, basic equation that you can see. First is basically the specific impulse. Now, when you talk about propulsion system, we talk about specific impulse, because the specific impulse is indeed, it's a value, or rather it's a measure of efficiency of a particular engine. A very high specific impulse would give you a very, very good amount of efficiency. That means the engine could be very small, but it gives you a good amount of thrust. So that is important. So that is the reason, if you look at it, it's basically nothing but the actual thrust with respect to your fuel usage. That is how it is done. Right. Now, velocity increment, delta V. So in one hand, when you are looking at any propulsion system, you will ask what is the specific impulse for this. It's very important, because once you have the specific impulse, you will actually inject it in this particular formula. This formula is called a rocket formula, rocket equation. Basically, you use this rocket equation to find the actual delta V. Or delta V is what? The velocity increment. The velocity increment that we need basically for a spacecraft to move from one spot to another spot. And what is the velocity increment and what we need to do, that you will learn in space mechanics. In satellite technology, if I need a certain delta V, who is going to give me? The answer is my propulsion system is going to give me. That is, you should be able to answer in satellite technology. Okay, but the actual calculation is you'll be exposed to when you do rocket, for example, rocket technology. So it's nothing but it's a specific impulse times by gravitational pull, ln starting mass and end mass. So you know that when you start the mass, you have a fuel, you burn the fuel, then the end mass, the mass would have to minus with the actual fuel that you burn. It's very easy equation. You should be able to get how much of delta V that you have won, or rather that you have provided. Okay, go on. All right, now different propulsion system. Again, what we are going to look at here, different propulsion systems, specifically for satellites. Specifically for satellites, and here is what actually is commonly used. First one is a gas motor, cold gas motor. So that means cold gas. The actual term is also tells us cold gas motor. So most probably there might not be actually a chamber to burn. You don't need to actually burn. So there is no combustion chamber. So instead of combustion chamber, you have a plenum chamber for gas pressure stabilization. So you have high pressure. Okay, so for that actually you have another chamber, but there is no burning taking place. Okay, there's no burning taking place. So thrust is basically from as low as 0.1 up to about 1000 Newton depending on the mission. Look at that specific impulse again, very important, 30 to 70 seconds. It's not too high, because we don't need a huge amount of specific impulse to do an orbit correction. We don't need that. Normally, if you look at it, these are the very compact ones. Fuels are propane, nitrogen, argon gas. It's in a gas form, and power supply 5 watt dedicated for active correction. So you see, so 5 watts means what? You need the actual electrical power basically in order to ignite. So that's what it means. It's a simple what is that diagram. So this thrusters, note these thrusters, you see every time comes to the pair. If you want a rotational motion, you must have a pair. Just like what I've said, if you want to rotate this body this way, you must fire up, you fire down, same thrust, that means the same Newton, then you can actually rotate this body, rigid body. Go on. Second type, chemical type. So chemical type, the first one is monopropellant. That means monopropellant, there's only one type of fuel that you use. And this is what type of fuel that here we have. We have a catalyzer or even electrical heating element in order to heat up the fuel. Thrust is basically 0.1 up to about 10 Newton. It's not too big. Specific impulse but better. Specific impulse better means that you can imagine that for small amount of specific impulse, you get a better amount of a small amount of fuel, you get a better amount of thrust. And the engine is technically is smaller compared to the earlier example, which is coal gas. Okay, this is what it means. And typical fuel that we use, hydrazine, N2H4. N2H4 hydrazine is a very typical fuel that you use in satellite. And then you use a power supply also here, 5 watt, 10 watt. So can you imagine you're harvesting energy from sun through the photovoltaic cells, you're generating solar power. Then after that, you need to also inject that solar power into practically your altitude or rather your propulsion system. You need that power. So this power comes from another system. This power comes from our power system that we have learned in the previous chapter. So this is quite typical in a geosatellite. Again, geostationary satellite is just like our MEASAT, 36,000 kilometers of altitude. It's a huge satellite, helicopter satellite. So you have this kind of options. So all these, I look at that. These are all thrusters. They come in pairs. All this, they come in pairs. You see, look at all this roll, pitch, yaw, east-west, roll, yaw. All these are basically the rotational motion that you want to correct, or the translation motion that you want to correct. For example, west and east, west and east. You will learn these all these terms. You will learn in space mechanics. All right, go on. Now, chemical motors also. You have a bipropellant. Bipropellant means that you have actually two fuel, basically one fuel and one oxidator actually. So with the combustion chamber, so you have two items, you need a combustion chamber to put them together. So thrust is about 10 Newton, it's quite typical. Specific impulse, quite nice, about 300 seconds. Then what about the fuel? The fuel option that we have is monomethyl hydrazine, very typical fuel in satellite. A lot of satellites are flying with MMH. And oxidator, you will have a nitrogen tetroxide, N2O4. So you have a fuel, you have an oxidator. They are different tanks. They will be actually put into together. Okay. Then you need the power 5 to 10 watt. Why? Heat up fuel, heat up the actual burning process. Dedicated for altitude or orbit correction. Now, this bipropellant is very common. Very common in satellite. Go on. Okay, another type is hybrid type. Now this hybrid type is not very common for satellite, but the system is like in existence. There are actually experiments done. Okay. Now what is hybrid type? Solid and liquid systems together. We put. Now remember, if you fly a rocket, the boosters that you see, central core, normally is a chemical engine. The side is normally a solid boosters. So those solid boosters are basically is what actually is mentioned here. But you can actually have a system where solid boosters and basically the liquid system is together. So that's this example here. No combustion chamber because you don't need one. Reason being, the solid booster is basically it'll be burned. So you don't need. So the fuel oxidator pumped in, then you have this fuel as a solid booster, solid. So this get actually connected with the exact oxidator. You just burn, and then your thrust is to this direction. All right. If you look at the options that we have, polybutene PP. This is quite typical for even the rocket boosters. Oxidator, again we can use the same one, nitrogen tetroxide, N2O4. Additive, you can consider this as for your additive corrections. Okay, also. Go on. This is a very, I would say, popular, in fact, electrical propulsion when we start actually talking about interplanetary mission. So why actually it's so popular? Because of because of only one single thing, because of the actual specific impulse. If you look at the specific impulse that we've been talking about just now, is about 280, 290, 300. But if you look at the specific impulse for electrical propulsion system, is thousands. So in this case, this is about 2,500. So when you have when you do an interplanetary mission, you need to travel very far. So therefore, your delta V needs to be quite a lot. So in order for us to have a high delta V, one of those ways basically is technically speaking to have a very high specific impulse. You have seen in the formula. So when you want to actually fly very, very high, that's the reason satellites or rather spacecraft with electrical propulsions you see very, very common in a deep mission. Okay, Deep Space One, for example, mission. So you have all this electrical propulsion system. All right, here simple. There's no combustion chamber. You have a voltage source for heating. Thrust is quite low. Why thrust is quite low? Because we can actually play around with the specific impulse, so it's fine for us. Fuel is not typically. Sometimes we can use hydrogen, hydrazine, N2H4. Power supply. The biggest disadvantage of ionic propulsion, or rather electrical propulsion, here is basically after motors are the high requirement of power. The power, you need a lot of actually electrical power. So this, you see, in terms of kilowatt, even 1 kilowatt is almost need for a satellite for 500 kilogram. That's what you need. So it's a showstopper, always very, very high amount of power supply needed. Why high amount of power supply? Because this process. Now, if you look at it, this whole system, how it works basically, it works on actually the Fleming's right route. Okay, right hand route. So you have electrical flow. You will have electrical flow. So when you have electrical flow, you will have actually two poles, anode and cathode. So you will have electrical flow. You can imagine. So when you can have a coils here, you call it magnetic coils, which produces actually magnetic field. So you have two coils already. You have two items ready. The electrical field. You have a magnetic field. The next, these two fields come together. What you will have a motion. So your right hand rule applies. So you have these two, practically your motion is going to go and give you a thrust. So it works on that principle actually. So that is the reason the electrical field, we need so much of electricity in order to actually provide that actual electrical field, so that you can have a very high amount of thrust. Now typically the good news for this kind of system is quite compact. That's the reason it can produce a very good amount of specific impulse. But unfortunately, in order for me to actually use the system, I need to pump in a lot of actual electricity. So that is a disadvantage. So in Earth-bounded missions, all those Earth observation, your small satellite, flying laptop, CubeSat, etc., you wouldn't find an electrical propulsion or even arc jet motors for as an option. So again, if you want to fly in Earth-oriented mission, you may want to actually look at the bipropellant options that we have. You can use typically hydrazine, monomethyl hydrazine, MMH, and an oxidator. You can use N2O4, which is nitrogen tetroxide. We go on. Another options that we have also quite good in terms of specific impulse. In fact, actually it's better. This is ion thrusters. Look at the amount of specific impulse that you can have. About 10,000 seconds. 10,000 seconds is super efficient. Thrust is very low thrust. But here, what is interesting is that power supply is very much lesser compared to the arc jet just now. So about 300 watt. So if you want to do interplanetary mission, you want to fly very, very far, ionic propulsion might be one option. How this actually works, again, there's no propulsion. You can imagine that the amount of electricity is needed basically to push, or rather to have that ionized fuel. Okay, the fuel will be actually ionized here due to the voltage, a very high amount of voltage that we have here. And then you can actually have, once you have the source here, there is a guide. Means like what? You always imagine the fuel is basically always ionized. So it is just waiting to be, well, I would say moving. It's waiting to be moved. So what exactly happened? There is a guide here. Guide means it's just like a chamber. Okay, it's like a chamber. It is a guide. Practically, you have a like a lane, and this would be also a negative grid. You have a positive grid. What exactly happened? You'll be attracted to this glide. So the faster actually attracts, then pumps out the actual gas back. So that will actually give you a thrust, and your rigid body actually can move up. So it's a very very interesting I would say option when you want to actually look at interplanetary mission. Argon gas is normally used as a fuel, or xenon gas. I guess we will stop here for the propulsion system. We will continue with the rotational motion with an attitude control system. I will going to explain to you maybe things like reaction wheel, so that you know how these actually two subsystems are helping the satellite in order to the satellite to survive in its orbit through two motions, rotational motion and translational motion. Propulsion system is going to give us translation motion and rotational motion, and the next chapter we are going to look at the purely rotational motion.